The energy behind the internet, from corrosion to the battery in your hand. Think about what you're doing right now. You may be watching this on a mobile phone, a tablet or a computer. You can send information across the world in seconds, receive an answer almost immediately, watch a video, store information and communicate with someone thousands of miles away. But where does the energy come from that makes all this possible? The answer takes us back to something much more fundamental: electrochemical energy. The device in your hand is powered by a battery, and that battery converts chemical energy into electrical energy. The voltage may be small compared to the enormous systems we normally associate with energy, but the principle is incredibly powerful. The same electrochemical principles that allow a battery to produce electrical current are closely connected. In fact, they're exactly the same as the processes that corrosion scientists have been studying for generations. This is where our work becomes interesting. A battery and a corrosion cell share fundamental electrochemical principles, and electrode chemical reactions can produce or consume electrons. Those electrons create an electrical current, while the surrounding electrolyte allows ionic charge to move through the system. In corrosion, the unwanted electrochemical reaction causes a metal to deteriorate. In a battery, we deliberately control the electrochemical reactions so that useful electrical energy can be obtained from them. And this raises an important scientific question. If we can understand and measure the current produced by an electrochemical reaction, can we understand the energy system more precisely? This is one of the reasons why we have developed the Alexander cell. Conventional corrosion measurements often concentrate heavily on electrode potential and the electrical conditions associated with equilibrium. Our objective is to go further by directly measuring corrosion current at the corrosion cell level. Current is particularly important because it provides a direct indication of the rate at which electrochemical charge is being transferred. That brings corrosion science directly into the wider study of batteries and energy technology. The same fundamental disciplines, electrochemistry, thermodynamics, material science, measurement and electronic control, are involved in understanding how energy is generated and transferred. The difference is that in corrosion we normally want to stop the electrochemical reaction, whereas in a battery we want to control it and use it to deliver useful energy. Now consider the extraordinary economics of this technology. The amount of energy required to perform an individual digital operation may be extremely small, but billions of operations take place continuously across the world's telecommunication systems and computing infrastructure. The internet, therefore, depends on enormous physical systems, servers, data centers, telecommunications networks, cables, routers, cooling systems, and electrical power infrastructure. These systems require real energy and continuous investment to operate. The question is not whether energy is free, but how efficiently that energy is generated, transferred, stored, and ultimately paid for, and by whom. This is where I believe corrosion science has a much bigger role to play than it is normally given. If we can measure electrochemical current more accurately, understand the energy relationships involved, and then use electronic systems to monitor and control those processes dynamically, we can begin to connect corrosion engineering with the wider science of energy management. Our objective is therefore not to claim that corrosion creates the energy used by the internet. Our objective is much more interesting: to demonstrate that the electrochemical principles behind corrosion are part of the same scientific foundation that allows us to understand batteries, electrical energy storage, and electrochemical technology. The Alexander cell gives us a practical way of investigating this relationship. By measuring corrosion current directly and then combining those measurements with electronic monitoring and dynamic control, we can move from simply observing corrosion to studying the energy and charge transfer processes that drive it. This is the direction of our dynamic corrosion control program: observe, measure, model, experiment, and control. If we can understand the smallest electrochemical cell, we can begin to understand much larger energy systems. And if we can learn to control unwanted electrical reactions, we can potentially extend the life of pipelines, infrastructure, batteries, and other technologies that depend upon electrochemical processes. So when you pick up your phone and connect to the internet, remember this: behind the screen is an enormous physical energy system, and inside the battery that powers your device is a small electrochemical system governed by the same fundamental science that we study in corrosion. That is why we believe corrosion science is not simply about stopping metals from deteriorating. It is part of the much larger science of electrochemical energy. And that is the question we want to investigate scientifically. How far can we take our ability to measure, understand, and control electrochemical energy? If you want to follow this work as we develop it, please subscribe to the channel and share the video and give us a thumbs up, and join us as we continue this investigation.
Yay!